So I was thinking today I could talk a little bit about how space-time is composed of quantum state vectors, these little vectors of light that I was describing in my last video, and how the vector is light. The rate of change of the quantum state vector is describing curvature or gravity, and also the rate that information flows, because there is information contained within the angle of the vector, and the rate that the vector changes is the rate that information is changing. So the reason why that's important is because there's something called Lorentz invariance. When you start approaching close to the speed of light or very high velocities, you start getting time dilation, length contractions, and it causes problems. But since these quantum state vectors that are emitted from entangled black holes onto a qubit are like zeros and ones, the cosine squared of the angle of each quantum state vector gives you the probability amplitude. In other words, it tells you the probability that the qubit will be in a spin up or a spin down state, or a 0 and a 1 like in a computer, or a pixel that is on or a pixel that is off. And we see the behavior, and we see relativistic behaviors, from light and things moving at very high velocities, and that causes an issue with Lorentz invariance. But what quantum information holography says and shows and demonstrates is that underneath that, the informational content is just zeros and ones. And since the information is just zeros and ones, it doesn't change. It's naturally Lorentz invariant regardless of the observer's frame of reference. And so light itself, when viewed as information on qubits, is naturally Lorentz invariant. And there is no theory besides this that is naturally invariant. And it's naturally invariant using the most fundamental thing, and that is light. And so that is why it's important to look at this in terms of information. Because as we were talking about before, the angle of the quantum state vector, that encodes the velocity of that qubit as a percentage of the speed of light. But that's just one snapshot. One moment later, the quantum state vector is emitted again, and if it changes, that gives you an acceleration. And even if it doesn't change, that means no change in acceleration. That means acceleration is 0, and that's when you're out in space where there's no gravity. But what's important about that is that when you look at just one snapshot of the universe, just one picture frame, that gives you all the quantum state vectors, and that gives you the velocity. But you cannot calculate acceleration without having a change in velocity. So you need two picture frames, two bits of information compared to each other, one snapshot of a quantum state vector and another snapshot, to give you a rate of change. And that is what gives you gravity and curvature. So what it means is that gravity emerges from the information field, because the information field, one snapshot, it is an information field, but it doesn't describe gravity. Gravity comes and emerges from the rate of change of the information field. So information is what's fundamental, and gravity emerges from it. It's pretty darn cool.